Hello students, welcome to my YouTube channel RD Academy. So in this video we will be learning about section 1.9, that is electric field lines. So in previous videos we have already seen the qualitative and quantitative treatment of electric field. Now we will learn a little bit more about the properties of the electric field lines itself and how they are usually represented in physics. Okay, so now let me consider a positive point charge. Okay, now will there be nothing surrounding this charge? So you cannot say there is nothing surrounding this charge, because as we have seen, whenever a charge is at rest, due to the presence of this charge itself, the environment near it will have electric field line, so that when you bring another positive charge plus q, it will repel or attract. Okay, that electric field exerts an electric force on the nearby neighboring charge. Now this electric field lines is just a way of seeing how the electrical environment around a charge looks like. Okay, so now assume this charge is situated at the origin of the xy coordinate system. Okay, so this is the xy coordinate system and the positive charge is situated at exactly the origin of the coordinate system. Now in order to represent the electric field lines due to this positive point charge, we need to take certain factors into consideration. Okay, firstly, we know that electric field is given by 1 by 4 pi epsilon naught, the charge magnitude divided by distance square multiplied by the direction of the distance. So now you can say that it is directly proportional to magnitude of the charge, inversely proportional to square of the distance from where you are measuring it. So it is like saying, due to this positive point charge, consider this point, it is near, and consider another point B here. Okay, in point A and point B, which point will have greater electric field strength? Obviously point A, because electric field is inversely proportional to the distance from the point where you are measuring it. Okay, so point A is closer to the charge, so R is lower, E will increase. For point B, R is greater and hence E will decrease. Okay, so keeping that in mind, now we need to see how the electric field lines are drawn. Okay, now see this magnitude of charge q is not changing, so that remains the same. Now while drawing the electric field lines, all we need to take into consideration is the inverse dependency of the distance. Okay, so what we will do is, when it is near to charge, I will draw long vector. As you move away from the charge, what happens, that length of the vector will keep on decreasing. Okay, like actually if you see in the textbook, it is given as for a positive point charge, electric field lines are radially outward like this. It is a continuous line, but you should know how that continuous lines are obtained. Okay, those continuous lines are obtained by joining these vectors. Okay, so whenever you are using vectors to represent electric field lines, you should remember that as you move away from the charge, what happens, the magnitude of electric field reduces. That factor is represented by the length of the vectors. Here length of the vectors is directly proportional to magnitude of electric field. As you move away from the charge, what happens, vector length decreases, electric field strength also decreases. This is what we have learned in the formula also. Electric field is inversely proportional to square of the distance. So if I were to draw along one vector along this direction, it will be like, here it will be larger length. As you move away, what happens, that the length keeps on decreasing. In a similar way, at every point there will be electric field lines. There will be one electric field like this and another one like this. And similarly at every point, what happens, you will get electric field. Now what happens is that if I join these lines, then I will get this orientation, that is straight line. Now you can ask me, like, now that inverse dependency is lost, no sir, like if it is one continuous line, how will we say that with increase in distance electric field strength is decreasing? When you use continuous lines to represent electric field lines, at that point you should start to use the density of electric field lines. Okay, when you are using this break lines or several vectors to indicate the strength of electric field, the length is proportional to magnitude electric field. But when you use the continuous electric field lines, at that point what happens? The density of the electric field is proportional to magnitude of electric field. Now listen, this point is very close to the charge, right? So if I were to draw an area of 1 meter square, then how many lines are enclosed within that area? There are 2 lines. So the strength is relatively higher. But if I move away from this charge and I draw one area here, so with increase in distance to the area, what happened? The number of field lines enclosed by that particular area also decreases. So the density of electric field lines indicates the strength of the strength of the magnitude of the electric field. So the points which are closer to the source charge will have high electric field. As you move away, there are no field lines passing. Okay, here the strength will be relatively lower. You cannot say it is zero, because see, here one line will be penetrating like this. Okay, but relatively what happens here? Now there are 4 lines penetrating the area, but here there are only 2 lines penetrating the area. So as you move away from the charge, what happens? The strength of the magnetic field keeps on decreasing. Okay, now we need to study the pictorial representation of positive charge, negative charge, 2 positive charge, 2 negative charge, and a positive negative charge system. I will deal with that in a due time, but before that let me share one important question, important 3 marks question from your board examination point of view. The question goes like, mention the properties of electric field lines. Okay, now can you answer this question? The first and foremost property is that the electric field lines, for a short I will write it as EFL, the electric field lines always start from positive charge and end on negative charge. Okay, do not use these symbols, write positive and negative in words only in your exam. Now I am writing like this due to space constraint. Okay, what is the first property? For a positive charge, electric field will originate. If you keep a nearby negative charge, what happens? This electric field lines will terminate there. They always start from positive charge and end on negative charge. Second one, what is the second property? In a charge-free region, electric field lines can be taken to be continuous curves without breaks. Now, what do you mean by the charge-free region? Charge-free region implies that there should only be one source charge. Okay, there should not be any other charge in the vicinity of this. So, in charge-free region, electric field lines are continuous curves without break. Like this, they form a continuous curve. A straight line is nothing but a curve. It is a special type of curve. Okay, so they are continuous curve without having any breaks. That is the second property. What is the third property? The third property is that the 2 field lines originating due to a charge, either it is positive or negative, they can never intersect like this. Okay, so what happens? Why it cannot intersect? Because if they were to intersect, then at this particular point of intersection, if you bring another positive test charge, it has 2 directions to move. One is it can move in this direction, or it can move in the another direction. So that is not possible. Coulomb's law tells you that the charge should move only along the straight line joining the 2 point charges. Okay, so 2 field lines, 2 electric field lines cannot intersect or cross each other. This is the third property. The last property is that electric field lines do not form any closed loops. So what do you mean by that? They do not form any closed loops. As you can see, they always, if you have a plus and negative charge system like that, they should start from positive charge and terminate on the negative charge. Okay, they cannot form a closed loop like this. They should start and end. They should have a starting point and they have a endpoint. So that is your fourth property. The fourth property is that they do not form closed loops. Now one question arises, why they cannot form closed loops? Because if they were to form closed loops, they would violate the conservative nature of electrostatic force or electric field. Okay, this will be more clear when I deal with electric potential in the second chapter. Okay, so for time being, just remember electric field cannot form closed loop because they would violate the conservative nature of electric field. If they were to form closed loop, what happened? They would violate the conservative nature of electric field. Okay, so for time being, remember these 4 points, and they are very important for your examination. The first point is that electric field lines start from positive charge, end on negative charge. Second point, in a charge free regions, that is, if you have only one charge, electric field lines are continuous curves without any breaks. Okay, now third point is two electric field lines cannot intersect or cross each other, because if they were to cross each other, what happens? At the point of intersection, they will have two possible direction to move. Okay, but Coulomb's law tells you that the charge can only move in one direction, that is along the line joining the two charges. Okay, the fourth point is they do not form closed loops, because if they were to form closed loop, they would violate the conservative nature of electric field. To conserve electric field, they should not form any closed loops. Okay, so while writing these points, please be careful while writing the spellings. For example, this continuous curves, intersect spellings, if you make a mistake in there, then you will lose marks. Okay, and this is one of the most important 3 marks question from this chapter, properties of electric field lines. Okay, now there is another one important question from this chapter, that is pictorial representation of electric field lines. This is also given in your textbook, but I will briefly explain here. Now take a positive point charge. How will the electric field lines look like for this one? As we have seen earlier, if I use continuous straight lines, then the number density will indicate the strength. Towards the charge, there are more number of lines. As you move away, there are fewer number of lines for a given area. So for a positive point charge, electric field lines are radially outward like this. Okay, similarly for a negative point charge, how will the electric field look like? Here also it is continuous curves, but now they are radially inward. Okay, electric field should start from positive charge and they should end on negative charge. So all the lines will come and end on this negative charge. They will start from the positive charge. Now for a pair of positive and negative charges, what do you mean by a pair of positive and negative charges? Instead of one, now you have two positive or two negative, but both should be like charges. We will discuss the unlike case also. Now what will happen if you have two positive charges? See, for this positive charge, everything should be radially outward. Draw that here. But now when you come to this side of the surface, what happens? Here you have one electric field line like this and another one traveling in this direction. So both will repel. So now you will have like this bent structure. Okay, initially they both were straight, but due to the repulsive nature, what happened? They will bend like this. Okay, this is the nature of electric field between two positive point charges. There won't be any electric field here. Okay, for like charges. Similarly for unlike charges also same thing. The outer end will have straight lines like this. For a negative charge it is radially inward, but for the inner end, what happens? For them also it is inward only, but now they will be curved like this. Okay, this is the situation for a pair of positive or negative charges. Now the last case for a dipole. Now briefly I will explain what is this dipole is. A dipole is a system of positive and negative charge. Both should have equal magnitude but separated by a small distance. The magnitude should not vary. How will the electric field lines look like for a dipole? Draw the outer surface nature first. How will be the electric field lines for positive charge here? It will be radially outward. For negative charge, it will be radially inward. Now, between these charges, how will it look? From electric field line first property, they should always start from the positive charge and end on the negative charge. So it will be like this. They started from positive and end on negative. Here also what happens, you will get one field like this. They start from positive and end on negative. Here also start from positive and end on negative. Okay, and here what happens, they will have various curves like this one, radially outward. Here it will be radially inward. Okay, in here there will be infinite number of electric field lines. So this pictorial representation, be careful. Okay, for point charges it should be straight lines. For a positive charge it is radially outward, negative charge radially inward. For like charges there will be no line between the two charges. Only for unlike charges you will have the line, and you need to show this curved nature also for the like ones, and unlike ones you will have curves like this. This is what you mean by the okay, this is how it will look like for a dipole. So this completes electric field lines explanation in detail. So in this particular section, this property of electric field lines is very important, and also the pictorial representation is also important. Okay, so we will continue with the next video. Thank you.